All right, I have started my graphing problem. Um, so these are the two graphs, and just a heads up, you're checking shape here. Shape looks great. You do want to label this with numbers and the name of the variable, and then the last thing you need is to clarify which graph is which. So this top one is the Chips Ahoy, and the bottom one is the Great Value. And what I'm noticing is that they're centered similarly, but that this one's definitely more variable, so that might have some kind of effect on our conclusion. But let's go ahead and say both of these are symmetrical. No outliers. So that is what I'm liking about this. It's giving me clues that maybe this is coming from some kind of normal population. All right. Lastly, 10%. These are definitely less than 10% of all of each type of cookie, each brand of cookie. So that's not a worry at all. The other thing you want to mention for this one, this might be a good time to start calling this condition something else. This is called the independence condition. And that means that for the two samples, that they're not connected in any way. So each number of chocolate chips is independent between the two brands, something like that. So are these truly two separate samples? There's no connection between them. That's independence. All right. So we're good on the conditions. It's time for our confidence intervals. So we're going to need some numbers. I'm going to have to run the just a warning on this one. I don't recommend using the calculator number because it's going to be very, very hard to go back and figure out what critical value it used for which degree of freedom. So I'm doing a 2-sample t interval, option 0, 10. So I have a list. I have two lists that have the data in them. So I'm going to tell it what the lists are. So list 1 contains my Chips Ahoy data. List 2 contains the Great Value data. One of everything, please. And are we doing a 99% confidence interval here? Okay. Never say yes to pooling for means, and it won't ever ask you for proportions when you need it. So calculate. Pooling for means is making an assumption that they have the same standard deviation, which they absolutely do not if you look at those two graphs. All right, so we're not going to use this degree of freedom, which means I'm not going to get that result exactly. But here are the numbers that I'm going to need for the calculation step. So I have to get the mean number of cookies for Chips Ahoy, 18.4. The mean number of cookies for Great Value, 19.4. The standard deviations for the Chips Ahoy is 1.7. Let's do 1 decimal, so 1.8. Standard deviation for Great Value, 3.6. Sample size for both is 10. Okay. And then what I wanted to say is I do need to make a choice about degree of freedom. So what I'm going to do is I'm going to say degree of freedom is 10 plus 10 minus 2, which will give me a degree of freedom of 18. And that is very good. I'll be able to look this up on the t-distribution chart because I need to get my critical value. And I'm doing a combination of degree of freedom 18 and doing 99% confidence intervals. So let's go ahead and grab that off the sheet. So this is not a t-distribution. That's a normal curve. It's shaded left. T-distribution is shaded right. So degree of freedom 18. I got that. So I'm looking at the 99% one, which is here. It's going to tell me how many stimulations left or right I need to go to be 99% confidence. It's saying I need a critical value in t of 2.878. Double check if that was my 99. It was 18. Okay. So this is the part the calculator will have done differently. It used 13.1 as its degree of freedom, so we can't really match it. But you can compare roughly the size you get. It should be about the same. So I'm doing a critical value of 2.87. Okay, so I'm going to pull it all together. So what I'm going to need to do for that is to estimate mean for the Chips Ahoy minus mean number of chocolate chips for Great Value. I'm using the observed difference that we saw, so 18.4 minus 19.4. I'm adding and subtracting 2.875 times standard error here, which is the standard deviation for the first one, 1.8 squared over the sample size, and the standard deviation for the second one, 3.6 squared over the sample size. So I'm going to get this number first. That's what I got. All right, so then I'm going to multiply those two to figure out my margin of error. So it's standard error, critical value, together it's a margin of error. This difference is a -1. So when I multiply them, I'm adding and subtracting 3.66 chocolate chips. And the average difference of chocolate chips from brand to brand is -1. So then when I'm done with this, I'm going to have a -4.66 and a positive 2.66. And I think the calculator, when I ran that interval, had a similar opinion about what kind of thing I would get. So let me just take a look at that again. Takes a while to run this one. It's pretty funny. Okay, so yeah. The calculator is about in the same area as me, but it had a different degree of freedom, so it's using a different critical value. So that's why they're not the same, just a heads up. Okay, so lastly, we're going to write our sentence. We're going to say we are 99% confident that the true mean difference in number of chocolate chip cookies, chips, between Chips Ahoy and Great Value cookies is between, and these are numbers of chocolate chips, -4.7 and 2.7 chocolate chips. And then there's a follow-up question. The follow-up question says, does your interval provide convincing evidence that there's a difference? Actually, guys, it does not. The number 0 is in our interval. So we're going to say for part B, since 0 is in the interval and is a plausible value, a possible number you could get, there is not evidence of a difference. This is saying you can get positive differences, you can get negative differences, you can get no difference, so no real discernible difference.